Maybe what are complex numbers first? Sorry? Imaginary numbers. Okay, what is an imaginary number? This arises from the need to resolve square root of negative numbers. Yes? This is something that we know very well from secondary school. Every time we have a square root of a negative number, what do we say? No real solutions. Correct? Why are we interested in b squared minus 4ac? Because it sits inside the square roots. If this whole thing is negative, we can just say, haha, okay, not my problem. No real solutions, I'm done with it. But this year, we cannot do that anymore, right? We have to address it. You can kind of see the real versus imaginary. Back then we say no real solutions, right? So what does it mean? There are imaginary solutions. Now they're okay with imaginary numbers, then what are complex numbers? Examples, right? Would be something like a 3 plus 5i. You will have a real component. This is real. This is the imaginary component. And I feel really bad every time I say imaginary because a lot of students think that this is just some made up part of mathematics, right? It's probably not useful. Mathematicians satisfy the need to solve equations. But let me assure you that it is something that is very, very real, as in terms of applications in real life, right? Like Wi-Fi, 5G, anything that has to do with signals, compression of data, right? You will need this. So this over here, we'll say is a member of the complex numbers. Okay, whereas previously we'll see something like 3 is a member of the set of real numbers. It's like an upgrade over the real. How do you think we can add complex numbers? How do you add these two together? Okay, you add the real. Okay, so you'll get a 4 plus AI, right? Subtract I think is a bit trivial. Let's say we take the green minus the blue, you get 2 plus 4i. That's okay, eh? Let's talk about multiplying. How will you multiply this? Treat it like what? Yes? Treat the I as like an x. Yeah, okay. So we just expand like we do, right? Like this, and then distribute this, yeah? Okay? Yeah, okay, let's try this out. Plus 12i squared. But what is I squared? I squared is -1, right? Remember that if I is equals to this, then I squared must be equals to this, right? So it's -12. It's equals to -9 plus 12i. By the way, if you don't believe this, you can take out a GC. First, you need to know where is I. Where is I? Anybody found it? Second. And decimal point. Very good, right? Okay, so let's do exactly that. 1 plus 2i, the blue and the green one. 1 plus 2i times 3 plus 6i. And you get this. So it works exactly as we expected to. Just very quickly, in case you're in a different mode, right? You realize that you have certain modes over here, right? Where we have the real, right? So if you're in a real mode and you do anything like a square root of -5, you'll just get a math error or something like that, right? If you put a plus bi, it means that if you do a square root of -5, you get square root 5i. Yeah? And then we have one more form over here, which is out of the syllabus, fresh from this year, right? So we don't need to care about this one, right? It's in the Euler form. Any questions? Yes, questions. Then I have a question. How do you divide? Divide is easy with the GC. Let's just key in, right? Let's do this one. Long division. So how do I start? Should I put a 1/3? Oh wait, it's exactly 1/3, right? Oh, this is a very convenient example. Okay, let's change, okay? Let's change for the sake of this, right? For the sake of discussion, right? What if it's 5i? Subtract, there's a 0, and this will be a 1/3 i. So does it mean the answer is 1/3 with a remainder of 1/3 i? What does that mean? This long division gives you this result, but I still have a problem, right? What is this? So it just feels like you're kicking the can down the road, right? Like if you see litter on the floor, you don't pick it up, but you kick it. Well, you don't have to pick it up, but as you walk forward, you come to the same problem again. Do you pick it up? Right? You're having the same division problem again. So how do you deal with this? So let me introduce to you what we should do. And it's surprisingly something that you've done before. Then what you want to do is you want to conjugate. Does this sound familiar? What's conjugate? How do you rationalize surds? Oh, you multiply by root 3, right? Okay, if it's a bit more complicated, 1 minus root 3. Can I just multiply by root 3 to the top and bottom? Doesn't work, right? What do I need to multiply now? 1 plus. And this 1 plus has a special name. It's called a conjugate. It's like a special version of the one before, right? But it has a plus instead. What is the effect of doing this, by the way? Why does this work? Because this is now in the form of a minus b, a plus b, which will give me an a squared minus b squared. And I'm very certain a squared is not a surd, and I'm very sure that b squared is not a surd. And that's why rationalization works. Okay? So in the same way, we're going to conjugate here. 3 minus 5i, very good. And why does that work? Can you think about it for a while? Why does it work? There you go, right? Then you're going to get an a squared minus b squared, right? Where this is like an a plus b, a minus b. And I know that a squared is real. I know that b squared is going to be real. I like to call this realize your denominator, right? There's no such term, I made it up. Just deal with the bottom first, right? The bottom will be easy. 3 squared minus 25i squared. 13 plus i over 34. Okay, and your calculator will put it as 13 over 34 plus 1 over 34i. So if you key into your GC, you get a string of like numbers here, right? But just to show you, the real component of this complex number is 13 out of 34, and the imaginary component is this one. Do we rationalize surds, by the way? Okay, so we know these two things are the same.
Then you'll be dividing by a fraction.
Very good, because this one would require you to do this, right? Is this easy to do? How about this one? This is... there's a difference. Correct? We are good with dividing by whole numbers. Okay? So the same, I would say, goes for complex numbers. Why do we want to make the denominator real? Would you know what this is equals to? Would you have thought, oh yeah, it's 14 out of 34 plus 1 out of 34i? No way, right? But if I give you something like this, you can tell me straight away what this is. This is 1 over 5 plus 2 over 5i. Okay? And that is why we want to make the denominator real. A few more things that we need to talk about. So we have notation. A is equals to 3 plus 5i. Okay? So when I put in RE of A, it will tell me 3. Because what this does is just to take the real component of a complex number. So if I put in this, I'll get 5i. To isolate just the real or the imaginary component. You can represent them here. How will you represent them actually? Say 3 plus 5i, where will you put it? Will you be able to represent them here? It's a bit strange. Okay, these are no longer x and y axis. These are the real axis and the imaginary axis. This is 3 plus 5i. Okay? Yes. So I'll pause here. I think the number one question in your head is, why does imaginary numbers get its own axis? By the way, you also need to know that this is called the Argand plane, right? Or Argand diagram. Now, why does it replace the y-axis? Right? It turns out, if you do this, we have very, very nice mathematical properties that we can exploit later on. Right? Let's go into the notes. Okay. So here's a sequence of increasing powers of the imaginary number. What is I to the power of 0? I to the power of 0 is equals to 1. Yes, because you can think of this as negative 1 to the power of half to the power of 0. It's just negative 1 to the power of 0. It's 1. I to the power of 1 will just be I. How about I squared? that is equal to -1, yes? So you can sort of see a map, right? Like a one-to-one mapping. Then let's look at I to the power of 3. You can think of this as I squared, I, and I squared is -1, isn't it? So it's -I. How about I to the power of 4? It goes back to 1. Do you see any pattern over here? If you go I to the power of 5, I to the power of 6, is there any pattern? Here's something you can do to sort of imagine what's going on. Can you see? Okay, so that's I to the power of 1, I to the power of 2, it's a bit slow. It's kind of like a rotation. I to the power of 3 would be another rotation. I to the power of 4, again we rotate. I to the power of 5, and you just keep on rotating. How will you describe this pattern, by the way? If you had to put it in like words to someone who has not done complex numbers, right? What would you describe this kind of pattern as? Recurring, right? It's like a 4-stage cycle. Do you know of something similar to this that has a pattern that keeps repeating and repeating? Actually, you do, right? This is 1, -1, 1, -1, 1, -1. This is a 2-stage cycle. You can use something like this to describe things in real life, like whether the light is on or off. You can go through a 2-stage cycle of on and off. Is there anything in life that goes through a 4-stage cycle? Huh? Sorry? The life cycle of the stages, alright, of the life cycle of an insect. This property is quite useful. You might see later on. It's actually linked to one of the topics that you already covered, right? I'll let you think about it, right? See if you can figure it out. Let's try this out. You can definitely use a GC, but I don't want you to use a GC. The solutions are over here. Okay, so one thing to discuss is, would you be able to guess? Like if I cover the answer, right? Like just looking at this, would you have expected this as the answer? Is it something that you can eyeball like, yeah, definitely 71 minus 19i. And this one? Okay, how about division? This is like simple numbers, right? 1, 2, 3, 4. Would you have expected this? Right? So these are things that are not that intuitive. But for now, something to think about. Are the following two situations possible? Situation number 1 is if I have a complex number and I multiply with a complex number, is it possible to get a real number? Situation number 2, is it possible that I have a complex number, I multiply by a real number, and I get a real number? I see some people nodding their head, right? Which one is possible? Number 1 is possible. Why is number 1 possible? We actually just saw it, right? What did we do? When we square or when we realize the denominator, that's exactly what we're doing, right? Yeah, this is possible, definitely. Yes. The second situation, is it possible? In a very layman way, why is 2 not possible? Why do you suspect 2 is not possible? Okay, let's say we have like a 3 plus 5i, right? Then we multiply with, say, 4. And then we need to multiply the I with another I to sort of cancel it out, right? Yeah? So you can notice that this is also somewhat similar to like scalar multiplication, like vectors, right? I'm just stretching the 5i component by 4. Illustration of what's happening is, if I have a component that's I like this, and I multiply by a real number, I'm just going to make it either longer or in the opposite direction. Or maybe, yeah, you can multiply by 0, right? And then it sort of like stays here, and arguably that would be real, I don't know. But if you do multiply any other numbers, you're not going to make it real. So this, number 2, is not possible. And hopefully now you start to appreciate the beauty of like an Argand diagram. Otherwise, this will be impossible to prove with the infinite complex numbers and the infinite real numbers. How do you know? Well, I studied vectors. I know this is not possible. This will be really important later on. Yeah. I'll give you some time to absorb this. Yeah? So here's a very good question. But out of the infinite complex numbers, is this the only one? Then can you give me examples of other complex numbers? Or is this really the only one? You see, so the way to answer this question is not by trial and error, it's by understanding this thing. So when you multiply complex numbers, right, something is happening over here. But I will not talk about it because it's just very slightly out of the syllabus, but yet you'll be tested on it. You have to know what is the effect of multiplying complex numbers on an eigenplane. You need to know the geometrical representation of multiplication of complex numbers. Okay, so we'll talk about that later. But now, let's move on. Let's think about this, right? Hey, real numbers and imaginary numbers are just like my vectors, my unit vectors I and j. They point in different directions. No scalar multiple of any of them could be made to turn into the other direction, right? So orthogonal is something like a 90 degrees, yes? So that also lends to the idea of the eigenplane, like, okay, I kind of get it why, like I is 90 degrees to the real axis. Hey, so here's a complex number, and usually we like to do this, right? We like to denote complex numbers with z or w, yeah? Okay, let z equals to x plus iy. Okay, and we'll say that x and y are real numbers. Okay, so this is how you see a typical definition of a complex number. So I tell you that the square of this complex number is equals to this complex number. Then can you work out what is the complex number that results in this? So this is how you do it. In the exams, right, you will do it for GC, right? And it's a lot faster. But I think it will also only give you one answer. If you expand the left-hand side, you should get something like this. Then we can compare the real and imaginary parts. This looks a very bit strange, right? To someone who does algebra. He says that, hey, how many unknowns are there over here? 2, right? X and Y. How do you solve for 2 unknowns with only 1 equation? But you did. Why? Why is it that you can solve? So it turns out that this thing, the real component and the imaginary components, right? They are like 90 degrees from each other. They don't affect each other. So whatever is the real component on this side, right? Let's call this the real component on the left-hand side must be equals to -5. And then the imaginary component of the left-hand side must be equals to 12. And that is very strange, something that we've never seen before. One equation can solve 2 unknowns, but because of the way complex numbers work, right? The real and imaginary really don't mix together, okay? Like water and oil. So if you are stuck with something like that, think about comparing real and imaginary parts, okay? You find that, hey, I have insufficient information. This is probably what you need to do. So the solutions are this, okay? And then of course you can use your GC and test it out, right? Okay? Alternatively, right, if you want to do this with a GC, all you need to do is just square root this, okay? But you realize that when you square root, okay, you only get one answer. Okay? So you should be smart enough to know that there is actually 2 answers. Why are there 2 answers? Is there anything to suggest that the square root of a complex number has 2 possible solutions? What if there are 3? Or if there are 4? How do you know? Right? So it's a bit strange, but we'll see that again from the eigenplane later on.